Make them famous, you can't.
What's your name? David. I have the opportunity to once in a while.
Stay in play with
They've done a lot of town stuff, like sounds.
Okay, let's get started. Let me have your attention. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker. But before I introduce today's speaker, there are some students that I would like to recognize. Each year, some of our students compete for and win, compete nationally and win scholarships, and it happens every year. And this year we have 3 scholarship winners from the American Nuclear Society, and they provide money, cash, and also a nice certificate. And so I want to ask these students to think 2 of the 3 are here today. First of all, there's Thomas Miller, who is the recipient of the Everett P. Blizzard Scholarship. It's for graduate students. Thomas, come down here. Congratulations. Thank you. And then the second one is the American Nuclear Society Decommissioning, Decontamination, and Reutilization Division Scholarship Award. I should mention that Thomas's award was $3,000 for graduate students. This is a $2,000 award. And the winner is Jennifer Cole. Jennifer, would you come down here? And then there's one other award. And I think this student has a class and couldn't be with us today, but let's recognize him anyway. It's Kevin Taylor, and he is the recipient of the A&S John and Muriel Landis Scholarship Award. And this is a $4,000 award. So even though he's not here, let's give him a round of applause. Okay. Now we can get on with the introduction of today's speaker, who is Dr. Lee Robertson. Lee is a research staff member in the Center for Neutron Scattering at the Oak Ridge National Laboratory. Lee received his Ph.D. In physics from the University of Houston in 1991. He also received an undergraduate degree in physics from Clemson, and he promises not to say anything about the Peach Bowl, okay, last year's Peach Bowl. After his Ph.D. in 1991, he had a postdoc appointment at the National Institute of Standards and Technology in Washington, D.C., for almost 2 years. And then he joined the Oak Ridge National Laboratory, the Solid State Physics Division, in 1993, and he's been there ever since. For those of you who don't know, the Solid State Physics Division eventually became the Condensed Matter Sciences Division, and now, just recently, his group moved over to the Center for Neutron Scattering, which is his present position. The title of this presentation today is Neutron Scattering. What is it all about, and what can it do for me? Ladies and gentlemen, please welcome Dr. Lee Robertson.
I'm going to be talking about, what is neutron scattering? How do you generate the neutrons? What do you do with them? How do you detect them? And, what kind of science can you do using neutron scattering as a technique? So let's see. Let me first maybe just make a statement about what neutron scattering is. It's essentially a probe that's used to investigate the structure and dynamics of materials on an atomic and molecular scale. And what you're really trying to do is you ultimately want to understand the bulk properties of the material, but a lot of times it's the microscopic characteristics that determine what the bulk or macroscopic behavior will be. And in a typical neutron scattering experiment. This is just schematic. Almost all neutron scattering instruments will be some variation of this. You have neutrons that are produced in a source, okay, and they go down some type of beam line, which defines the neutron optics. They interact with your sample, and then they're scattered to a bank of neutron detectors, and you measure the angle that the neutrons are scattered by when they interact with the sample, and you try to determine the change in the neutron energy when it interacts with the sample. It'll tell you two things. It'll tell you about the atomic structure of the material, and also tell you about the dynamics of the material. So let me move on by going over some of the properties of a neutron. Why would you want to use neutron as a probe to study the structure of materials? The first characteristic will be that neutrons don't have a charge. They're neutral particles. This means that they're highly penetrating because they have low interaction potential when they're passing through matter. It's a non-destructive probe, and because of the high penetration capabilities, the neutron beam, when it's passing through your sample, you can send it through very complicated sample environment chambers. Like you make a very high temperature furnace, has thick walls, lots of heat shields and all, and the neutron beam can get in and out without being attenuated too much. And neutrons have a magnetic moment. That means the neutrons not only scatter from the nuclei in the atoms, they also interact with the unpaired electron spins. So not only can you probe the arrangement of atoms in material, you can also probe the arrangement of the magnetic moments on the atoms in the material. And you can do both measurements simultaneously, so you can see the correlation between the two. And neutrons have a spin. That means when they interact with the nucleus of an atom, you can have both coherent and incoherent scattering of the neutrons, and you can use that to your advantage when you're trying to separate different processes that are going on in the material that you're probing. And last, the neutrons interact with the atomic nuclei as opposed to, say, X-ray or electron scattering, where the interactions with the electrons. And this means that the neutrons are very sensitive to light elements. For example, hydrogen has one of the largest scattering cross-sections for thermal neutrons, whereas X-rays and electrons don't interact so strongly with hydrogen because it would either be a naked proton or only have one electron, typically. And you can exploit isotopic substitution because if you have a composite material and, say, the two components both contain nickel, you can tag one material with one isotope of nickel and the other material with a different isotope of nickel, and neutrons will see those two nickel isotopes as two different scatterers, whereas most other probes are not sensitive to that, and you couldn't tell the difference in the scattering pattern from the two components. Let's see. Now I move on to the two most important characteristics of neutrons and why they're so widely used as a probe for atomic cell structure is that thermal neutrons, when I talk about thermal neutrons, I'm talking about neutrons between, say, 1 millielectron volt and maybe 200 or 300 millielectron volts. For me, 100 millielectron volt neutron is a high energy neutron. Okay, this is because of the relationship between the neutron's energy and its wavelength. What you want is the wavelength of the neutrons to be on the same order as the scale of the structure you're trying to study. Okay, that gives you the highest resolution and the greatest amount of information. And neutrons in the millielectron volt range have a range of wavelengths. Here we're into the regime of that wave-particle duality thing where you use the neutron energy is equal to h bar omega, and you can work out that for millielectron volt neutrons, the wavelength range goes from about 1/10 of an angstrom. I'm going to use angstroms here rather than nanometers because that's how I think, and I'll screw up what I'm saying if I try to do it in nanometers. And these very short wavelength neutrons are at the higher energy end, okay? And the high energy neutron, remember, for me, high energy is about 100 millielectron volts. You study, it's good for studying amorphous materials and liquids and gases. You look here, that's all components. You got the glass in the mug, and the beer is a liquid, and the foam is a gas, and you can study those going out to larger aminotransfer, which would correspond to this wavelength range. And as you go to slightly longer wavelengths, a little bit less than 1 angstrom, this is in the regime where you can study the typical regime for studying atomic crystal structures. And moving on, you go to a slightly longer length scale, and now you're getting the regime of setups where you can study porous media and flow through porous media, that sort of thing. Move on up the scale, you can study precipitates, and then grain structure materials, both the physical grain structure of a polycrystalline material and also the magnetic domain structure of a magnetic material. And last, you get the really long wavelengths, the order of 30 or 40 angstroms. You're getting the wavelength of neutrons is getting up to the size of small biological structures. So you get to where you can study the interrelationship of, say, viruses and other biological structures. And the second thing is that when you work with neutrons in this wavelength range, the energy of the neutrons is on the same order as the energy involved in dynamical processes in materials. For example, there's actually a reciprocal relationship here. The long wavelength neutrons down here are actually correspond to the low energy neutrons over here. But when you're talking about really slow dynamical phenomena, you need very low energy neutrons for lots of long wavelengths. You can study things like diffusion in materials. It could either be diffusion of a minority species in a liquid or propagation of ions in a solid state ionic conductor. And then you move on up in energy, you get to rotational motion systems. Like imagine you had a crystal composed of a packing of these atomic clusters, and on the lattice, these atomic clusters can actually rotate or librate or something. In this energy range, you can probe the dynamics of that. Then you move on to magnetic fluctuations in the crystal. If you imagine you have all the magnetic moments are pointed out like this, and a magnetic excitation goes by. It's like doing the wave over in Neyland Stadium. The magnetic moments do this. And the excitation will pass by, propagate on down. You can study those dynamics using neutrons in this energy range. Here, study photons, which is slightly higher energy. That just corresponds to vibrational modes in the material, which is related to the speed of sound and the thermodynamic properties of the material in general. And finally, you come all the way around from diffusion, all the way over to diffusion. This is just diffusion at the other extreme. Whereas here, we're talking about stuff actually penetrating and moving through material. And over here, I'm actually talking like something like a hydrogen atom trapped in a cage type crystal structure. The hydrogen can sit there and vibrate very fast at very high energy, and eventually it may hop over to the next cage and actually disseminate through the material that way. That's typically a very high energy process. Okay. Okay. The next thing I want to talk about is how do you produce the neutrons that are used in these experiments. I'll go down the list, how they're produced, how they're detected, and then what you use them for. So don't listen to anything you've heard from Quaker Oats. You can't just buy a box of neutrons and dump them out on the table and do this kind of experiment. It actually turns out that you need a neutron flux on the order of 10 to the 15th neutrons per square centimeter per second near the source, so that you can propagate out a collimated beam of neutrons to use in your experiment at the sample. Because you want to get at least 10 to the 7th, 10 to the 8th neutrons out to the sample. So you lose that much going from an isotropic source to the collimated beam that you're going to use in your experiment. Okay, and there are really currently only two types of neutron sources that can deliver this kind of flux. First is the reactor sources, which typically use diffraction to determine the wavelength and energy of the neutrons. And the second is spallation sources, which typically use time-of-flight techniques to determine the wavelength and energy of the neutrons. And these two sources are very complementary. Types of experiments that work well at a spallation source are different from the kinds of experiments that work well at a reactor. Okay. So let me talk about a little bit first about reactor sources. The Center for Neutron Scattering, where I am, is located at the HIFER, which is the high flux isotope reactor at ORNL. And this is our core configuration. The actual fuel goes here, okay, and it's surrounded by a beryllium reflector, which reflects the neutrons back into the core, and that sustains the chain reaction. And this out here is all pool water down inside the pressure vessel, and then there's an additional pool out here filled with water, then a big concrete biological shield on beyond that. And what the crazy neutron scatterers do is we drill a hole all the way through all the shielding, all the way into the beryllium reflector to let the radiation out so we can do our experiments. Okay, these are the 4 beam tubes we have at HIFER, HP1, 2, 3, and 4. And they have different configurations and different characteristics. And this is beamline HP2. This is what my instrument is on. And here, this region right here corresponds to the top of the pressure vessel, right along there. Okay, and right here, you can see the Cherenkov radiation just emanating from my beam tube, which is coming off the aluminum in this region right here. Okay, that's the blue glow you see down in there. We've never had a beam tube that glowed before. So this is part of the upgrade of the neutron scattering facility at the HIFER, and we've optimized the coupling to the neutron source such that we now have enough neutrons coming down this beam tube that it gives off the Cherenkov wave. And this is HP4. In HP4, we're introducing a liquid hydrogen cold source, supercritical hydrogen, and the neutrons, when they come out of the core, are far too high in energy, the order of big MeV, to be useful for any of the kinds of work that we do. So here, in the beryllium reflector, it acts like a flux trap. Okay, look on this chart over here. The edge of the reflector is right there. Okay, so we drill in from the outside. We put the tips of our beam tubes here at the maximum flux in the flux trap. This solid line here is the flux of thermal neutrons on that plot. And it's a log plot, and of course this is distance going out from the core center line. Okay, so at the reactor, that's how we pull off the thermal neutrons using the experiment. And in here is just a photograph of that was taken when they were lowering the new beryllium reflector into place. We have to replace the beryllium in the reflector about every 10 years or so because it swells and has embrittlement from all the radiation damage. And that's a photo that was taken the last time it was put in. Okay, so that's how you generate the neutrons at a reactor source. And this is just a schematic of the instrument layout that's going to be how it's going to be when the HIFER facility upgrade project is complete. Don't try to read all this text. I'll just point out that the thermal type instruments are located in here, close up to the reactor. These are instruments that work, say, at 10 millielectron volts to 100 millielectron volt range. And I forgot to say, this is very important. Here at HP4, we're putting in this cold source, and the neutrons that come out here and are thermalizing in the reflector will pass through this liquid hydrogen. This is the vessel here. It's at the end of the beam tube. Pass through the liquid hydrogen and scatter inelastically in the liquid hydrogen, and the mean energy of the neutrons will be reduced. It'll drop from about 300 kelvins down to about 7 kelvins. So 70 Kelvin. So think of it as a Maxwell distribution. The peak for the thermal spectrum is about 310 kelvins, and the peak of the neutrons coming through the cold source is about 70 kelvins. So the peak wavelength has moved from, say, 1.5 angstroms down to, or up to about 6 angstroms. Okay. So, there we go. So these are the thermal instruments here. We're looking at the Maxwell distribution that peaks at about 1.5 angstroms. And these are what we call the cold instruments out there that are looking at that cold source in the HB4 beam tube. And they're using 6, 8, 10, 20, 40 angstrom neutrons for their work. So you have to, like I was talking about in the beginning, you have to match the wavelength and energy of neutrons to the length scale of the system that you're studying. So that's why the instruments are divided up like that. Okay. Now, I'll move on to spallation neutron sources. This is a diagram showing the layout of the S&S that's currently under construction at ORNL. And here, I just want you to see the overall structure. The method for producing neutrons is quite different. You start off with a ion source here, usually H minus. That's what they're going to use. And then, since it's a hydrogen atom with an extra electron, it has a charge, and you can accelerate it down through here. At the end, it passes through a foil. I don't remember which foil they're going to use at the S&S. It's typically either aluminum oxide or gold, or something like that. They'll strip off both electrons. You're left with just a naked proton coming on through, which now is also a charged particle. So you can send it over here to a synchrotron and build up the flux. Okay, and when you're ready for a pulse of neutrons to come to the instrument, I was also point out that spallation neutron sources are pulse sources. Reactor sources are steady state sources. That's an important distinction I failed to make earlier. When you keep shooting pulses in here, and they're synchronized with the pulse is already in the synchrotron, when you build up a big bunch of protons, it comes through here, and it slams into a target. Okay, the impact of the protons into the target, which is typically a heavy metal, spews out neutrons, and then they have beam tubes or beam paths coming in to capture those neutrons, just like you do at a reactor. So let's see. I'll go into a little bit more detail about that. Here this is a mock-up or a diagram showing the target at the S&S. And the target is actually in this region here. Okay, the protons are coming from over here. Okay, when the protons hit the nuclei in the atoms of the target, the S&S is going to be mercury. You have several processes take place. Imagine this is a proton hitting a mercury nucleus, and it really wallops it when it hits. And initially, it knocks off some nucleons, and some of those will be neutrons. And it also instigates an internuclear cascade, which promotes that nucleus into a very excited state. It corresponds to some astronomical temperature for the nucleus. And then you get a second process. There are actually many processes that take place, but the next dominant process will be what's called boil-off, where the nucleus will drop back down to a lower energy state, and it will just spew out all kinds of stuff. And again, a lot of what comes out of it will be neutrons. Okay, and typically for each collision of a proton with a nucleus, you wind up generating 25, 30 neutrons. Okay, but then those neutrons come out and they interact with the rest of the nuclei in the target. So from that 25 or 30 that you generate from the collision of the proton, you might actually get, I don't know, 4, 5, or 6 neutrons actually make it out to contribute to the flux coming from the source. But just like at the reactor, with these spallation neutrons are even higher energy than the reactors from the fission in the core of the reactor, the neutrons from the fission in the core of the reactor. So analogous to our beryllium reflector, they put these moderators around the source. And neutron scattering instruments actually look at these moderators, not the target, as their source of neutrons. So it's just the same thing. These very high energy neutrons enter the moderator, become partially thermalized with it, and then leave the moderator and travel down the flat path to the neutron scattering instrument. There's another issue here for spallation sources. Since it's a pulse source, and you're using time of flight as a technique to determine the wavelength and energy of the neutrons, you want this, when the proton pulse hits the target, you want as sharp a pulse as you can, but also as many neutrons as you can get coming out of that pulse. Because if you look here, there's two kinds of moderators. There's the decoupled moderator and the coupled moderator. And if you look here in the moderators, they're surrounded by neutron reflectors. In this case, solid stainless steel and beryllium again. And in a coupled moderator, neutrons come in, bounce around in the moderator, bounce out in the reflector, bounce around in the moderator some more, and eventually come out. They could be bouncing around in there, and when you get way out in time, they'll tell this pulse. They're wandering around here going, hey, where'd everybody go? The main pulse is already taken off down the flight tube. And this gives you an uncertainty in the time that the neutrons originated from the source. And that translates into an uncertainty in the time it took the neutron to get from the source to the sample to the detector. And it's that time that's telling you the energy and wavelength of the neutrons. So you want this source to be, this pulse coming out of the source to be as sharp as possible. At the same time, you want to get as many neutrons as you can. So what they do is they'll put an absorbing barrier between the moderator and the neutrons coming back in from the reflector, and that will reduce the amount of time neutrons can take to get out of the moderator and on their way down the flight path. Because neutrons that come out from the reflector can't get back in, so they don't contribute. That's how you get this narrow pulse here. But you can see that it's quite a bit lower in flux than the coupled moderator. And there's a way to even get a narrower pulse. You can do what's called, you can poison this moderator, which you put in a low concentration of some neutron absorbing material. So now only neutrons that have a very direct path through the moderator really have a chance of getting out. If they take some circuitous path through the moderator, they have a high probability of being absorbed. Okay, so that's how you generate the neutrons and get them started. And then you talk a little bit about the time of flight technique. Okay, imagine this is your pulse starting at the moderator, and as it travels down the neutron beam line on its way to the sample, the pulses get broader, broader, and broader. Okay, because when you get down to here, the high energy short wavelength neutrons are over on this side of the pulse, and the slow long wavelength neutrons are over on this side of the pulse. Okay, that's how you use the time of arrival to determine their energy. The fast ones get there first, and the slower ones get there later. That's not so hard to see. And that's typically all you do in a setup where you're just doing diffraction. You're not interested in the inelastic processes. You just assume that all the scattering is elastic. There's no exchange of energy between the neutrons and the specimen. They just get scattered elastically. And then the scattering pattern tells you where the atoms are in the material. If you want to do inelastic scattering, not only do you need to know the time the neutrons arrive, you want to have as monochromatic or as uniform single energy group as you possibly can, because now the neutrons are going to arrive here at the specimen, and you'll take the time it takes to get from the specimen to the detectors to determine their energy change. Okay, you assume that they all arrive at the specimen at the same time and at the same energy, so you're only taking a tiny slice of monoenergetic neutrons out of this pulse, and then they interact with the sample, and then that little sharp pulse spreads out again. The ones that lose energy in the sample will take longer to get from the sample to the detectors, and the neutrons that gain energy in the sample will take less time to get to the detectors than the neutrons that scatter elastically. Hope that's clear. And then the question comes out: how do you pull out this little piece of the pulse and create a new, very a new pulse is very sharp in energy, they use what's called choppers. These are just a bunch of rotating wheels. You can see it here. It's a big wheel. There's a guy's hand for scale, and it has some slots put in it. They come in packages with several rotators. Okay, if you see up here, there are these windows. I don't know if you can see it. There's no contrast here. The neutron beam is passing through those spinning wheels, and it's all synchronized with the pulses, the proton pulses arriving at the target, so that when the pulse is flying through this thing, these holes in these wheels line up in such a way that only a very narrow energy pulse can get through. The rest of them get rejected. Okay, then it flies on down, interacts with the sample, and you measure the angle and the energy change coming out of the detectors. And that tells you what you want to know about the system you're studying. Okay, this is another diagram showing the instrument layout at the SNS, how it will be. And it's really not that different from the instrument layout at the reactor. You just have a cluster of instruments around. The protons come in from here, target is here, and then the neutrons are produced or gathered up in the flight paths coming out to the various instruments like that. And there's a whole zoo of different techniques being used here. Some of them are high resolution energy, high resolution spectrometers to measure inelastic processes, and some of them are do straight diffraction. Okay. Now, so that's how the neutrons are generated. They go down the flight path, interact with the sample. Now I would like to talk a little bit about how you detect them, because there's a problem with working with thermal neutrons, is that they're not that easy to detect. There are no high efficiency mechanisms to detect these low energy neutrons, at least with the positional precision that we require. So usually what you wind up doing is the neutron comes in and you depend on some nuclear process to convert the neutron into some sort of charged particle or photon. Okay, then you can use any type of detector that's used in physics and engineering to detect charged particles. And for neutron scattering, there are basically three types of detectors that are used. There's a helium-3 gas detector. Usually is a long tube filled with helium-3 gas and then some quenched gas, and just a wire with a potential down the middle of the tube. And neutron comes in, interacts with the helium-3 nucleus. The expectation value for this transition is very high. You wind up with two hydrogens of energy. Hydrogens are charged, and you get an ion cascade, and you can detect it on the wire in the tube. We also use fission chambers. This case, neutron will come in, it will react with a U-235 or something. You get there's a lot of different processes that can take place, and you get some fission products coming out, and the uranium, you usually have uranium hexafluoride or some gas, mixed with another gas, and the fission fragments ionize the other gas, and you detect those charged particles. And last, we use scintillators, where, for example, we have a neutron interact with the lithium-6, and once again, you get some charged particles and some photons coming out. Scintillators are fairly new on the scene for neutron scattering because of their high gamma sensitivity in the past. There are some new techniques going on where we use coincidence and wavelength shifting techniques to reduce the gamma sensitivity of the scintillation detectors, and that way we can get even higher efficiency detectors than, say, with the helium-3 gas detectors. Here are just some pictures. This is a neutron beam monitor. It's using it's a fission chamber. I think this particular one has uranium hexafluoride in it, and they're typically used for monitoring the flux of the beam coming into your experiment, because you can make them very low efficiency. You make detectors like this that have a detection efficiency of 10 to the minus 6 or so. And the reason you want that is the instant beam coming in is very intense, but you don't want that detector to attenuate the beam very much. You don't want to use up very many of your neutrons just measuring your incident flux. You want to save them and count them in the detectors that are measuring the scattering pattern of your experiment. And this is just a picture this is the VCS spectrometer at NIST. These are all individual helium-3 tube detectors. And I think in this particular instrument, there are 910 that wrap around the sample. And so you can get as much coverage of the 4 pi scattering coming off your sample as you possibly can to increase your detection efficiency. And this is a scintillator detector that's being developed. And this is one using the wavelength shifting fibers. I think this is a picture that came from Royal Crow, the SNS, actually. And the neutrons just pass through. It's usually lithium impregnated in glass. Some other compounds to tailor the wavelength. The photons just come out and they get channeled in these fiber optics over to a photomultiplier tube and count it. And you can get position sensitivity in these by measuring. You have fibers going this way, fibers going this way. If a neutron hits here, it will register that fiber and that fiber, and you'll know where the neutron hit the detector. And you can also get position sensitivity in these helium-3 detectors, where when the neutron comes in and the charge is captured on the wire running down the length of the tube, you can measure the time difference when the pulse reaches this end of the tube versus that end of the tube. You can tell where along the wire it hit. Okay. So now, after going through all this, you go to these huge facilities. They're very expensive to run. The instruments you put on them are very expensive. So you have to think to yourself, there's got to be an easier way to find out the same information. Okay? And if there is an easier way, you should use it. Right? Because neutron scattering is a very difficult technique to do sometimes. And other techniques that give you or similar types of information about structured materials are the usual other scattering techniques, X-rays, electrons, and light scattering. You also have NMR and Mossbauer spectroscopy, and then calorimetry and ultrasonics for directly measuring the thermodynamics. But when it comes to things like magnetism and being able to study the structure and the dynamics using the same technique at the same time, so you can be varying the temperature and see what's happening, a lot of times neutron scattering is the only way to go. And there are good and bad points about this. You know, we said that the neutrons are highly penetrating, as opposed to X-rays and electrons, where it's difficult to get the probe in and out of a very thick sample environment chamber. The sensitivity to magnetism, the fact that you study structure and dynamics at the same time, it's sensitive to low Z nuclei or atoms. You do contrast matching by varying the isotopic composition. Say you have a multi-component matrix made of several different materials, and you do a diffraction pattern, you just get this impossibly complicated pattern you could never understand, because you have material A interacting with material B with C, and C with D, and so on. But if you can sometimes do isotopic tailoring and do what's called contrast matching, you can make the scattering cross-section for materials A, B, and D the same, and have material C be different. Then it behaves like a two-component system. And if you're interested in what's going on in component C of the composite, you can pick that out much more easily. That's a very, very effective technique. And then again, it's non-destructive. You don't have to, if you want to see deep into a material, you don't have to cut it open to do it because of the high penetrating thing. But then also on the bad side, I also list highly penetrating. It's highly penetrating because the interaction of the neutrons with matter is weak. Okay, so yes, that means you can pass a neutron beam through a large thickness of material, but it also means that your specimen has to have a lot of atoms in it. It has to be big. Okay, because the interaction is so weak. It takes a lot of atoms in the material you're studying to scatter the beam. Typically, you need something like 30 or 40 grams for inelastic work, and half a gram or so for elastic scattering. There are situations where you can work, in the milligram quantities, but it's nothing like X-rays, where a 400 micron crystal would be considered large. Now here we're talking crystals or pieces of material or centimeters dimension. And the isotopes for doing the contrast matching are expensive. And the technique is non-destructive, but when you pass a thermal neutron beam through most materials, you wind up activating something. So your specimen is intact, but typically it'll be radioactive when you take it off the instrument. So it really limits what you can do with it after you complete the neutron scattering experiment. And the third thing is there are no compact neutron sources that have anywhere near the flux you need to do these types of experiments. So it means you have to write a proposal, send it in to be reviewed, and then you have to travel to some major facility to do your experiment. So I'll reiterate, you shouldn't use neutron scattering unless you're using one of its unique properties to study your system. Okay, if you can use one of these other techniques, you should, because it'll be cheaper, and you'll probably have a lot easier time doing the measurement. Okay. So now I'd like to, as I finish up, last 10 minutes, talk about some of the science that's done with neutron scattering. Because here we're doing diffraction. This is diffraction from single crystals. Okay. Well, over here we have a diffraction. This looks like a bunch of spots. Okay. And this is where you get a set of spots that correspond essentially to the Fourier transform or the spatial relationship of the atoms in the material. It's just that every atom material is scattering the neutrons, and if you think of the neutrons as waves, each atom in the material becomes a new source for the scattered waves of neutrons, and you get constructive and destructive interference. And you get these spots where the neutron waves constructively interfere. Okay. It brings to mind there was a very clever experiment done a couple of years ago by Sam Warner at the University of Missouri. We took a neutron beam from their research reactor there, it's called MERV, and he attenuated the beam down to the point where at any given time there's only one neutron inside the crystal. And the question was, do you still get an interference pattern? In other words, does a neutron scattering in a spherical wavefront from an atom interfere with itself? And the answer is yes, you do get a diffraction pattern. It's difficult to get your hands around that. It's a very good experiment. Get your head around that. Well, here's our example of diffraction. I picked a quasicrystal. This is interesting. Quasicrystals are aperiodic crystals. You know, a crystal you typically think of, it has two properties. It has translational periodicity. You have some motif, and you just repeat it over and over again to build up the crystal. And it also has orientational order, whereas the orientation of this motif is related to the orientation of the repeated motif infinitely far away. But in quasi-periodic crystals, you have the long-range orientational order, but you don't have translational periodicity. The thing is ordered, the structure is completely deterministic all the way out to infinity, but there's no translational periodicity. This is seen by the symmetry group that's used. These crystals will usually have either decagonal or icosahedral symmetry, and both of those symmetry groups have five-fold symmetry axes as part of the symmetry group, and five-fold symmetry is incompatible with translational periodicity. If you think about it in two dimensions, you have a plane, take a bunch of pentagons, and you try to pack the pentagons together in a plane without leaving any gap, any empty space between pentagons. You can't do it. So you have to decompose the pentagon into smaller subunits, and then you can pack those. But you can pack those in a way to maintain the five-fold symmetry, even though it fills space. That's what happens in these crystals. And they're very complicated to resolve. But you can see just the crystal by itself, the morphology, the overall morphology is a pentagonal dodecahedron. The pentagons actually stick out as the facets of the crystal. Then if you look at it with an atomic resolution microscope, which is what you see here, you can actually see the atomic clusters. We know from the diffraction pattern that this structure is built up as a packing of these atomic clusters. And if you look down at the tops of the clusters, you can see the little pentagon of atoms sitting on the top. And then if you analyze the position of all these diffraction spots, you can work out the structure of these clusters that are going together, packing together to make this thing. And indeed, even the little atomic clusters that make up this crystal are tiny pentagonal dodecahedra. So it's very, very interesting. It's just amazing the entropy of the atoms coming in to form these clusters and then forming the structure that has no translational periodicity. You know, as a physicist, you should ask yourself, how do the atoms know where to go when they put this thing together? You can't. It's hard to imagine any interatomic potential that could give you something so complex. Okay, so now I'm going to move on to powder diffraction, which is another technique where this is the technique you use if you have a powder or a polycrystalline material. Rather than having a single crystal like this, you have a bunch of tiny single crystals that are all randomly oriented. And what you want to do is you take this crystal pattern and just spin it. In each one of these diffraction spots, make a circle of all the different possible orientations of the crystal. Okay? And you do the same thing. This is also a diffraction technique. And you basically just do a radial scan out from this is the origin over here where the unscattered beam is. This is an angle, we call it 2 theta, moving out from the incident beam. So when you come to this angle, there's a bunch of neutrons scattered there where there were no neutrons scattered out of the point. You get to this angle, there's a bunch of neutrons scattered. And these correspond to those circles you would get in the other diffraction pattern if you rotationally averaged it. Okay, in this you have less direct information because there's no directional information here, so there's only one-dimensional information. So you have to build a model of your system and calculate the diffraction pattern from the model and compare it to what you measured and refine it that way. It's an iterative process where you go back and forth. This is a common compound hematite, iron oxide, and this just goes over the things you do to extract the atomic crystal structure from this diffraction pattern. The size of the unit cell is given by the position, the angle at which these peaks occur. The symmetry is given by some of the peaks that are will be allowed for a unit cell of this size will be absent, and they're absent due to cancellation in the interference pattern. That tells you symmetry. And then last of all, the relative intensity of these peaks tell you how the atoms are arranged on the lattice. Okay. Moving on to another diffraction technique. This is called residual stress. This is these are usually called engineering instruments, where this is an example of looking at a friction stir weld. Okay. This uses the power diffraction technique, but with a very specific application. You take like a big chunk of steel, okay, and it's been welded or bent or cold rolled or something. It has what's called residual stresses. I'm sure you all know of that within the material. And you use power diffraction to move a tiny gauge volume. You're only illuminating like a 1 millimeter cube inside this huge piece of steel at a time. And you actually measure the angle that the power diffraction peaks occur at. And you look for tiny changes in the d-spacing or the distance or look for expansion or contraction of the unit cell, which shifts these peaks a little bit. And you can actually map out the strain modulus inside a material that way. Here we're looking at a stir weld, where you just take you're joining 2 pieces of material, usually of aluminum alloy. You have some tool that comes down here and mechanically smears the 2 materials together, and welds them. And here they're using the residual stress diffractometer. And here, if you imagine turning this up on its side, so the weld runs that way. Okay, and they just went in and they measured the residual stress. It's red means it's under compression, and blue means it's under traction. Okay, and this is a model they had for stir welding. This is what they actually measured, the strain map. You see, they got very good agreement, which means at least somebody understands how it works, at least to some degree. Okay. Now we're going to magnetism. This is one of my experiments. So here we were looking at magnetic multilayers. These are used in the recording industry, and we were interested in the magnetic structure of an antiferromagnetic material trapped with a spin density wave trapped between 2 other antiferromagnetic layers. Spin density waves means you have your regular antiferromagnetism, which means magnetic moments of the atoms are up, down, up, down, up, down. And you enter a spin density wave, and there's 2 kinds of layers. There's pure chromium, the chromium doped with manganese. This is the chromium doped with manganese. This is the pure chromium with the spin-density wave. We're just interested in how the spin-density wave develops in the confined geometry sandwiched between those two dope layers. Okay, but all I really want to show you here is this is the diffraction pattern we measure, all the structure in here. You know, here's the real space model. You take the Fourier transform of this, and you get the red line. The thing here, the blue circles are the diffraction data, and the red line is the Fourier transform of this arrangement of magnetic moments. And that's how you can use the neutron scattering pattern to determine the magnetic structure. Okay. We'll get to the small angle scattering. This is a really cool experiment. They were looking at alignment of membranes. Okay. Where it turns out you take these polymer membranes and put them in what's called a shear cell. You have a stationary cylinder on the inside and then another cylinder on the outside. And the gap in between the two, you fill the liquid that has your polymer in it. And if you spin this really fast, you'll get the membranes to line up in sheets like that. Whereas at rest, they form this porous sponge-like structure. In this experiment, they were interested in determining the energetics, switching from one structure to the other. So when you start out, it looks like this. You spin it in this shear cell, and at the right velocity, the membranes uncurl and form these sheets like this. So now here, this is the small angle scattering diffraction data. This is what it looks like in this state. Then they turn the shear cell off, they stop it, and they watch the evolution as the structure transforms from this to this. Okay, these diffraction patterns are taken at 0.2 second intervals. This is happening very quickly. And by combining the morphological change you see in the small angle neutron scattering data with simultaneous light scattering measurements, they can work out what the activation energy actually is from transforming between these membranes to the sponge-like structure. Okay. Now move on to phonons. Like I said earlier, phonons are just vibrations in the crystals. And here we're looking at phonons in uranium. Uranium is very strange, has a very complicated phase diagram for a single element. And this is part of the stockpile stewardship program. We're trying to figure out what happens to uranium in containers, you know, if there's a fire in the storage facility or something. We're just looking, doing inelastic scattering. This is low temperature up to high temperature. And you see that the rise in low energy modes and the structure becomes more well defined at high temperature. This is exactly the opposite of what you'd expect. And this is presumably due to the energy degeneracy between the 5d and 4f electrons in uranium. This is magnons. This is looking at magnetic excitations traveling through crystals. See these magnetic moments are rotating around as an excitation goes by. You actually get a dispersion spectrum that looks like that, and you can actually work out what the magnetic exchange. You have the interatomic potential that's giving you the relationship between the atoms and the crystal, and there's a magnetic contribution to that. By measuring the force constants that govern these magnetic interactions, you can work out what the magnetic part of that is. Last system is diffuse scattering. This is also something that I work on, used to study disordered materials. Here, these little guys here are the Bragg peaks, or the usual diffraction peaks, and these are diffuse peaks. And you can look, this one's round, this one's more of an oval shape, this one's round, and you can study this, and you can look at the local environments about atoms in a disordered material. So the Bragg peaks here give you information about the average structure of the crystal, and these big diffuse blobs give you information about the local deviations from the average structure. So use that to study disordered materials. And then I'll just summarize that, like we said in the beginning, neutron scattering is a tool for probing atomic scale molecular length scale characteristics of materials, which hopefully help you understand their bulk properties. There are 2 types of high flux neutron sources, reactors and spallation sources. There are several neutron scattering user facilities in North America. 2 of them are in Ornell. I think there are about 5 total. And neutron scattering should only be used when its unique capabilities can be exploited. Thank you.
Okay. We have time for a few questions, comments. I have a question. You've given us a really good explanation and somewhat of a good understanding of neutron scattering, how it works. But can you give us some concrete, practical examples of how it's been used to improve the quality of materials, to develop new materials? Some real examples so that the students can relate to.
Let's see. The best example I can come up with off the top of my head is high-strength magnets, development of these iron boron silicon magnets, and that's what led to permanent magnets that are strong enough to, for example, operate your electric windows and make your the electric motors that make the windows go up and down in your car. Things like that were a direct result of this.
Okay. Any other questions or comments from the audience?
What about in
Radiography? Yeah, radiography facilities usually go along beside neutron scatter facilities. I've never actually done radiography myself, but the same source characteristics and the same optical coupling between the radiography instrument and the source were very similar. So I don't know, there was a person from Metals and Ceramic Division, Cam Hubbard, was looking at some point at building a radiography type station, one of the slant tubes at the HIFER, but I haven't seen any actual equipment show up yet.
Okay. Any other questions? Okay. Seems like we always have a few new faces each week, and need to remind everyone that we do have refreshments downstairs, and everyone is invited. And you can go down and talk more with Lee about neutron scattering. But before we adjourn for refreshments, let's again express our appreciation to him for his presentation today. Thank you. Yeah, well, Paul,
You're welcome.